Fluid pressure. After understanding the concept of thrust and pressure, and let's see how to describe the fluid pressure, the pressure inside the fluid and the pressure that is exerted by the fluid on the objects which are immersed in it. So this leads to the famous theories by Archimedes and Pascal. Let us understand the concept of this fluid pressure. So we know generally that the liquids have no definite shape. This is a well-known fact. But they take the shape of the container. This has no definite shape. But one thing about the liquids is, it not only takes the shape of the container, it also retains its volume. For example, if you pour 1 liter of liquid into a flat dish or into a cylindrical dish, the volume is still 1 liter. Let us take, for example, to understand the fluid pressure, a glass filled with water, and this is a glass, and we see that the water exerts a force on the bottom of the glass. Water exerts a force on the bottom of the glass on every square centimeter. If this is given in the centimeters, the dimension of the bottom of the glass, and every square centimeter it exerts force. Whatever the force it exerts, the water exerts on the bottom, gets distributed into each square centimeter. So we understand that the water exerts a force on the bottom of the glass, which gets distributed. Now remove the glass and freeze the water. Then we will get ice. So let us say in the same shape, we will get glass shape, we will have a frozen ice. So the weight of the ice cube is being taken or supported by the bottom of the ice cube. So the weight of the ice cube is nothing but the force. That force is being exerted on the bottom of the ice. It shows that in this case, weight, here it's a force, but both of them are equally exerting on getting distributed on the bottom of the glass here, bottom of the ice cube here. So the ice cube is able to stand. So we also know that force per unit area is pressure. So here, by saying in this example that the force is acting on the bottom on each centimeter square, we are basically defining force per unit area. So this is nothing but the pressure. So pressure is F by A, and F is P into A. Now let us take to describe how the weight of the liquid acts at different depths of the container. Now take a container and there is a liquid in it. This is a glass container and there is a liquid with a density of, let's say, d grams per centimeter cube. This is the density of the fluid, and the container's height is h. The container's height is h. Now imagine a column of 1 centimeter cube, a liquid column. This is 1 centimeter square area, that is the width and length is 1 centimeter square and height is h. So from this we understand that the weight of this column, what is the weight of this column which is acting on this 1 centimeter square? In this example, weight of the column on this 1 centimeter square is h, height into area. So h into, And on this 1 centimeter square, the force is, the density of this is D. So H into D. Because this HD gram weight is being supported by 1 centimeter square of the bottom. So this 1 centimeter square is the area of the bottom. So this is being supported by this entire column of height H, and the weight of this is H into D, that is the density. So weight of the column is HD, and we know that P is the force per unit area, which is nothing but the pressure. The pressure is force per unit area, which is nothing but HD, the weight of the column of liquid. The units become gram per centimeter square in this case, or kg per meter square, based on how the dimensions are given. Because pressure is defined as the force per unit area, and here the force is weight, and the weight is weight of the column of the liquid per unit area is given as HD. So weight of column of liquid, we are defining it per unit area in 1 centimeter square area. So it becomes HD. P is defined this way. How we arrived at this? Volume of column, 1 centimeter square column, is H into 1 centimeter square, which is H centimeter cube. Now the weight is of this column becomes H into weight of 1 centimeter cube. The weight is nothing but the volume, the 1 centimeter cube. So 1 centimeter cube weight multiplied with H will give you the weight of the column. Now weight of 1 centimeter cube is nothing but density. Hence the weight of column of liquid becomes H into D, which is HD. Basically on 1 centimeter square area over a height of H. So this is how we got to know what is the pressure applied or exerted by the liquid on a column of 1 centimeter square where the container is of height H. At any depth of the container, the pressure can be measured, and it doesn't depend on the shape of the container. Let us take, for example, we have a container and a container cylinder shape, and now liquid is filled in these containers, and both the containers are having the same height. So the height is, let's say, H1, and here also the height is H1. And let's take the point where at point A, let's say the height is H2. That means we want to see what is the pressure bottom of the container for these two. That means at the height H1. And we want to see what is the pressure at a point A at the same points of these two containers, which are H2 of height from the top. So pressure for bottom of these containers, at bottom of these containers the pressure is, height is H1 and D is the density, because we are filling it up with the same, let's say, grams per centimeter cube and grams per centimeter cube, same liquid in both the containers. So the pressure is H1 into D, that is the pressure at the bottom. And pressure at A, the point A, pressure becomes, the height is H2 into D, which is H2D. So we understand that the shape of the container makes no difference to the pressure of the fluid inside the container at different heights. It is the height that makes the difference, because the liquid is the same liquid carrying the same density. So therefore we understand that the shape makes no difference. And also we understand that the pressure in vessels of different shapes the same at equal depths of the container in them. So this is the equal depth H2, the pressure is the same H2D, and at a depth of H1 the pressure is H1D. And also the pressure, the height into the density, we understand that of the pressure of the fluid is the same, or let's say that is equal in all directions. From these observations, the great scientist Pascal came out with a law on pressure and the fluid pressure, which we will define now. Pascal's law states any increase on a fluid in a closed container will be transmitted equally to every part of the fluid. So we have got pressure as height into density, height of the container into density of the liquid, and we also said that at the same height for the same liquid, it doesn't depend on the shape of the container. And also we observed that the pressure of that water column in the example, and every centimeter square, the equal pressure is exerted. So in order to understand the Pascal's law better, let us take closed container with different diameters on both the sides. If we say this as a D diameter, we will say this as 4 times that of D. And we keep a piston here. This is a piston, and we'll keep a larger diameter piston here. Now there is a liquid with a density D grams per centimeter cube. Now we put a weight. This is a weight. Let us call it W1. So there is a closed container. One side, it's having a diameter D. The other side, the diameter is 4 times. And the liquid's density is D. And on piston 1, when we put a weight of W1, what happens? The pressure develops that gets transmitted to piston 2. Now when the pressure gets developed and it gets transmitted to piston 2, and it's a closed container, so what happens if we don't take any action on the piston 2? It will start coming up. So in order to balance both sides of the container, we will start putting weights on this. How many weights of the equal weight W1 will take care of the equilibrium status for this liquid? In this case, it takes 4. And why? We understand that this is a smaller surface, this is a larger surface. So, smaller surface of piston 1 with the one weight, the pressure or the force exerts on piston 2 will be larger compared to the pressure exerted or the force exerted on piston 1. The force exerted on piston 2 is much higher because the diameter is much higher. So it depends on the ratio of these two diameters. So, in this example, the diameter of piston 1 is small d, whereas diameter of piston 2 is 4 times d. So, for equilibrium, we have to put on piston 1, if we put W1 weight, then on piston 2, we need to put W2 weight. Why? Because any increase on a fluid in a closed container will be transmitted equally to every part of the fluid. So, this much of a fluid will get into this larger area of the fluid. So, the increase will be directly depending on the area of the fluid. So, we understand that from this example, if the container's area is larger, that much higher will be the increase in the force and indirectly the pressure. This is the principle which is used in hydraulic pressure. We know many equipments which work on hydraulic pressure. Hydraulic pressure uses the principle of Pascal's law and the principle of smaller force on smaller piston exerts larger force on larger piston. See, the smaller force on smaller piston, like in this example, exerts larger force on larger piston.